Okay, in this video, we're going to be looking at prime and composite numbers. And what we'll be looking at in this video is how to identify prime and composite numbers. We're going to look at prime factorization and also number of divisors. And we'll also determine if a number is prime. And then we'll talk more about primes. Okay, in this slide, you'll see that the following rectangles represent the number 18. Here we can do one row of 18 blocks, or 2 rows of 9 blocks, or 3 rows of 6 blocks. So as you can see here, the number 18 has 6 positive divisors: 1, 2, 3, 6, 9, and 18. Okay. Below each number listed across the top, we identify numbers less than or equal to 37 that have that number of positive divisors. Okay, so here we're looking at positive divisors from 1 to 9. Now in this case here, the number 1 only has one positive divisor. As you can see, this list has 2 positive divisors, and this list has only 3 positive divisors, 4, 9, and 25. Then this list has 4 positive divisors in this case. Here we got this one with only 1 positive divisor. 5 positive divisors, that's 16, and so on. So from here, these numbers have exactly 2 positive divisors. That's the number 1 and themselves. Like for example, let's say the number 13 has 2 positive divisors, 1 and 13. That's it. 31 has only 2 positive divisors, 1 and 31, and nothing else. Okay. And by the way, let me go back to here. This is what we call prime numbers here. The ones with exactly 2 positive divisors, those are the numbers that we call prime numbers. Now, with composite numbers, they have at least one factor other than 1 in themselves. So here, the ones that are circled in a dotted circle, those are called your composite numbers, because each one of them has more than one factor. And the number 1 has only one positive factor, and that's 1. It's neither prime nor composite. Neither prime nor composite. So here we got some definitions of what a prime number is and what a composite number. A prime number is going to be any positive integer with exactly 2 distinct positive divisors. That's the number itself and 1. That's it. A composite number is any integer that's greater than 1 that has a positive factor other than itself and 1. So a composite number has more than 2 positive factors. More than 2. A prime number only has 2 positive factors, positive divisors, itself and 1. Let's look at this example here. Show that the following numbers are composite. The number 1564. This is a composite number because I can divide 2 by 4. The last digit ends in a 2, so that tells me that 2 can go into 1564. And I believe 782 times. So in this case here, 1564 is composite. The number 2781 is also composite. Take the sum of the individual digits, which is in this case 20. 2 plus 7 is 9, plus 8 is 17, plus 1 is 18. 18 is divisible by 3. So that means 2781 is composite. What about 1001? Okay. Now, in this case here, you can take 11 and use that divisibility rule that we talked about in the last video and divide 11 into 11. You'll see that it's going to be a whole number. And in this case, 1001 would be a composite number. Now, what about this? The product of the odd numbers. 3, 5, 7, 11, 13. And then you're going to add 1 to it. Well, the product of those odd numbers are going to be odd. But then you add 1 to it, it's going to be an even number. All even numbers are divisible by 2. So in this case here, it's going to be composite. And in fact, all even numbers, with the exception of 2, would be a composite. Keep in mind, 2 is going to be the only even prime number in this case. Now let's talk about prime factorization. Students continue to develop their understanding of multiplication and division and the structure of numbers by determining if a counting number greater than 1 is prime, and if it is not, by factoring it into a product of primes. Okay, composite numbers can be expressed as products of 2 or more whole numbers greater than 1. Each expression of a number as a product of factors is a factorization. And a factorization containing only prime numbers is a prime factorization. Okay. Because in a prime factorization, all you're going to do here is just find nothing but a product of prime numbers. Okay, now here's the fundamental theorem of arithmetic, which is the unique factorization theorem. Each composite number can be written as a product of primes in only one way, except for the order of the prime factors in the product. Okay, that's the unique factorization theorem, because we can take any composite number and write it as a product of primes. And to find the prime factorization of a composite number, you're going to rewrite the number as a product of 2 smaller natural numbers. If these smaller numbers are both prime, you're finished. If either is not prime, then rewrite it as a product of smaller natural numbers. And you will continue this until all the factors are prime. Okay, and a couple of examples would be this. The number 84. Here we can break 84 up into 4 times 21, because 4 times 21 does give you 84. You want to start off with 2 numbers that will give you the product of the number that you're trying to find the prime factorization of. In this case, we can use 4 and 21. Neither 4 nor 21 are prime numbers, so we need to break those up into products of primes. 4 can be broken up into 2 times 2. The number 21 can be broken up into 3 times 7. Okay, so here 84 as a prime factorization using exponents will be 2 to the second, because you can see 2 is used as a factor twice, times 3 times 7. Okay, another example will be the number 495. Well, we can start off with 5 because I know that 495 is a factor of 5. It's divisible by 5. So divide 5 into 495, you're going to get 99. So you have 5 times 99. Now 5 is prime, but 99 is not, because I can break 99 up into 11 times 9. Now 11 is prime, but 9 is not. I can break that up into 3 times 3. And 3 is a prime number, so I'm done. So 495 in exponential form as a product of prime factors would be 3 to the second times 5 times 11. Okay, here's some more prime factorization examples here. The two trees produce the same factorization. I mean, the same prime factorization, except for the order in which the primes appear in the products. Like in the number 260. One way you can do that, break it up as 26 times 10, because 260 is a multiple of 10. Then 26 can be broken up into 2 times 13. 10 is broken up into 2 times 5. Or, since 260 is a multiple of 5, you can use 5 and then divide 5 into 260. That's going to give you 52. 52 is a multiple of 2, so 2 goes into 52 26 times. 26 is a multiple of 2. Divide 2 into 26, that's going to give you 13. Okay? So here you get the same prime factorization, but here the order is just different. We can also determine the prime factorization by dividing with the least prime, if possible, like using the number 2. If not, we can try the next larger prime as a divisor. And once we find a prime that divides the number, we continue by finding the smallest prime that divides that quotient, and so on. Look at the number 260. Well, 260, the smallest prime we can use is 2, because I know 0 is the last digit. It's divisible by 2. So divide 2 into 260, you can get 130. And again, the last digit is a 0, so we can use 2 again. Divide 2 into 130, that's going to give you 65. Now, we can't use 2 because the last digit is not a 0 or a 2 or a 4, 6, or 8. And we can't divide 3 into 65, nor can we divide 4 into 65. Let's use 5. The last digit is a 5, so divide 5 into 65, we're going to get 13. And since 13 is prime, you can divide 13 into 13. That's going to give you 1. So the numbers on the left-hand side represent the prime factorization of 260. And this one on the right side is the alternative form, but it's done the same way. Let's look at the number of divisors. How many positive divisors does 24 have? We're not asking how many prime divisors, just the number of divisors, or any divisors. So here, these are all of the divisors of 24. Well, since 1 is a divisor of 24, then 24 divided by 1 is 24, is a divisor of 24. 2 is a divisor of 24. That means that 24 divided by 2 is 12, so that means 12 is a divisor of 24. 3 is a divisor of 24, meaning 24 divided by 3 is 8. So 8 will be a divisor of 24. And 4 is a divisor of 24. That means that 24 divided by 4 is 6, which is a divisor of 24. Another way to think of this, think of the number of positive divisors of 24, is to consider the prime factorization of 24, which is actually 2 to the third times 3. Now, notice 2 to the third equals 8. That has 4 divisors. 3 has 2 divisors. So if you use the fundamental counting principle, there are 4 times 2, or 8 divisors of the number 24. Okay, and there is a rule that you can use to find the number of divisors here. If P and Q are different primes, M and N are whole numbers, then P to the N, Q to the M has N plus 1 times M plus 1 positive divisors. You'll take, in other words, you're going to take each individual exponent and add 1 to it. The N, you're going to add 1 to it. The M, you're going to add 1 to it. And then you're going to multiply the two together to come up come up with a number of positive divisors. And this is what this is in general. So in this example, you want to find the number of positive divisors of 1 million. If you do the prime factorization of 1 million, it's going to be this. That's 10 to the 6 for 1 million. Now the 10, we can write that as 2 times 5 as prime numbers. So you have 2 times 5, that product is to the 6th power. Notice that each number in the parentheses is going to be raised to the 6th power. That means the 2 will be to the 6th power, the 5 is to the 6th power. So for 2 to the 6th, it's going to have 6 plus 1, which is 7 divisors. The 5, the exponent is 6, so it'll be 6 plus 1, which is 7 divisors. Multiply 7 divisors for 2 to the 6 times 7 divisors for 5 to the 6, you're going to have 49 divisors. So the number 1 million has 49 divisors. Okay, another example would be finding the number of positive divisors of the number 210. Okay, we need the prime factorization of 210 first. Well, 210 will be 21 times 10. Well, it's not prime. 21 is not prime. 10 is not prime. So let's break 21. Break that up into this. 2 times 3 times 5 times 7. That whole product is to the 10th power. And each number in this prime factorization is to the 10th power. So you got 2 to the 10th, 3 to the 10th, 5 to the 10th, 7 to the 10th. And then you'll add 1 to each exponent and then multiply. So 2 to the 10 has 11 divisors. 3 to the 10 also has 11 divisors. 5 to the 10 again has 11 divisors. 7 to the 10 also has 11 divisors. So that's actually 11 times 11 times 11 times 11, or 11 to the 4th, which is 14,641 divisors. So 210 raised to the 10th power has 14,641 divisors. Now, we want to determine if a number is prime. There is a way that we can do that. And that is, we must check only divisibility by prime numbers less than the given number. For example, to determine if 97 is prime, we must try dividing 97 by the prime numbers 2, 3, 5, and so on, as long as the prime is less than 97. If none of these prime numbers divide 97, then we can say 97 is prime. So when you check, we determine that 2, 3, 5, 7 do not divide 97. Assume that P is a prime number greater than 7 and P divides 97. Then we can say 97 divides P also divides 97. Because P is greater than or equal to 11, 97 divides P must be less than 10 and cannot divide 97. And here's something general for that. If D is a divisor of N, then N divides D is also a divisor of N. If N is composite, then N has a prime factor called P such that P squared is less than or equal to N. If N is an integer greater than 1 and not divisible by any prime number such that P squared is less than or equal to N, then N must be a prime number. And note, because P squared is less than or equal to N, that implies if you take the square root on both sides of this inequality, we can say that P is less than or equal to the square root of N. That would be enough to check if any prime is less than or equal to the square root of N. Okay, that's if any prime is going to be a divisor of N. And let's look at this example. is the number 397 composite or prime. Okay? Here are the possible primes for P such that P squared is less than or equal to 397 are 2, 3, 5, 7, 11, 13, 17, and 19. Now, how do they get that? You have to take the square root of 397, which means your primes must be that you select must be less than, and if you do the square root of 397 on the calculator, you're going to get 19.92, which I'm going to say 20. Okay, so you have to test primes that are less than or equal to 20. And in this case, these are the numbers that you have to check. Those are the prime numbers that you have to check: 2, 3, 5, 7, 11, 13, 17, and 19. And if you take the time and try to do 397 divide 397 by each of these primes, you're going to come up with a decimal. None of the primes will divide 397, so that means that 397 is a prime number. Is 91 composite or prime? Okay, now, to do that, we take the square root of 91. That means your primes must be less than or equal to, the primes that you use must be less than or equal to, must be less than or equal to 10. And the primes that are less than or equal to 10 are going to be 2, 3, 5, and 7. That's all. Now, 2 does not divide 91. 3 does not divide 91. 5 certainly doesn't divide 91, but 7 divides 91, because 7 goes into 91 13 times. And because of that, we can say that the number 91 is composite. Okay, the next thing we'll look at is the Sieve of Eratosthenes. Here's one good way of finding all the primes that are less than a given number, and that's to use the Sieve of Eratosthenes. Okay? Here we're going to take all the natural numbers greater than 1 and place them in what they call a sieve. The numbers that are not prime are methodically crossed out or dropped through the holes in that sieve. The remaining numbers will be prime. And we're going to go through a Sieve of Eratosthenes, in this case, to find all the prime numbers that are between 1 and 100. Now here I have the list of all the numbers from 1 to 100. Okay? Now, what I'm going to do here is cross out numbers and then circle numbers in this case to show you how this works. First of all, we know that 1 is not prime nor composite. So we cross out the 1. Next, we're going to circle the 2. And then we're going to cross out all numbers that are divisible by 2. Anything divisible by 2 means they must end in a 2, a 4, 6, or an 8, or 0. So this column, the last digit is a 2, meaning it's divisible by 2, so we cross out this column. The 4, anything ending in 4 is divisible by 2 as well, so we cross out that column. All numbers that end in 6, that's this column right here, that's divisible by 2. Cross that out. And then this column, that's the 8, it ends in 8, is divisible by 2, so we cross out that column. And finally, anything ending in 0 is divisible by 2, so we cross that out. Let's cross out that column. So as you can see here, half the numbers are gone. Just about half the numbers are gone. All right, next we're going to circle the next number that's not crossed out. That's a 3. All numbers that are divisible by 3 are crossed out. So we see a 9 can be crossed out. 12 is already gone. 15 can be crossed out. 18 is crossed out. We can cross out 21. 24 is gone. 27 can be crossed out. 30 is gone. 33 can be crossed out. 39 can be crossed out. It's divisible by 3. 42 is already crossed out. 45 can be crossed out. 48 is already gone. 51 can be crossed out. 57 can be crossed out. Let's see, 60 is gone. 63. We can cross that out. 66 is gone. 69 can be crossed out. 72 is gone. 75 can be crossed out. 78 is gone. 81 can be crossed out. 84 is already gone. 87 can be crossed out. 90 is gone. 93 can be crossed out. 96 is already gone. 99 can be crossed out. So those are the multiples of 3 that are crossed out. Next, we can circle the 5. All numbers that are multiples of 5 can be crossed out. That means anything ending in 0 will be crossed out. Guess what? This column is already crossed out from the multiples of 2. So the only numbers that are left that are multiples of 5 are gone. That's in this column where the last digit is a 5. Okay, now we got 7. Circle the 7. Any multiples of 7 must be crossed out. Let's see. 14 is already gone. 21 is gone. 28 is gone. 35 is gone. 42 is gone. We can cross out 49. We can get rid of the 56. That's gone. 63 is already gone. 70 is gone. 77 can be crossed out. 84 is already gone. 91 can be crossed out. And 98 is already gone. So there are very few numbers left. And then the next one is 11, because that's the next number that's not crossed out. And I think all of the numbers, all of the multiples of 11 are gone. So we can go ahead and circle the remaining numbers. Now notice that the numbers that I'm circling in green are the prime numbers that are less than 100. Okay, and that's it. Let's hope I didn't miss any. All right, the ones that are circled in green are the prime numbers. The numbers that I crossed out are your composite numbers because those have more than 2 factors. Okay. All right, and here, this is a more better version of just that, which you can see here. Okay, and there are more prime numbers here because this only represents the ones that are less than 100, but there are more, and you can find some on the you look up the internet and find prime numbers, and then just look at some of the numbers that are bigger than 100 that are prime. Okay, so this will conclude this particular video on the concept of prime and composite numbers.